When we look at the lengths of covalent bonds, it has to do with the radius of those atoms, but it also has to do with how many pairs of electrons they share. The more sharing that happens, the closer those atoms have to be to one another. And so when we look at bond lengths, the thing that I want to draw your attention to is this box here at the bottom, right? That when we think about bond lengths, a triple bond is shorter because those two atoms have to overlap more than a single bond, where those atoms only have to overlap for a pair of electrons rather than 3 pairs of electrons. And so a triple bond is the shortest, double bond in the middle, and then single bonds are the longest. Right? And so if we're talking about nitrogen, a triple bond nitrogen is very close, very short. A double bonded nitrogen is a little bit further apart, and then a single bonded nitrogen is even further apart. The last part of this introduction deals with polar covalent bonds, and that's when we have a covalent bond where the two elements are not sharing that electron, those electrons, equally. In this case, we have here an electron-rich region, so lots of electrons, and you can see that it's red for negative. And over here in this electron-poor region, so this is lots of electron density is what we call it. Here in the electron-poor region, we have a little electron density. And this is the positive side of a particular bond. Now, positive and negative, they're not charged. Right? It's polar covalent. All that means is one of the two atoms in that bond likes electrons, has an affinity for electrons, more so than the other atom. We use electronegativity to describe sort of how much an element, pulls electrons toward it. An excellent example of a polar covalent kind of molecule is hydrogen fluoride. You can tell already that because fluorine has so many of these electrons around him, he must really like electrons. And it turns out that the fluorine is our electron-rich guy, and hydrogen is electron poor. Now, to indicate which end of this bond is kind of positive with fewer electrons and which end is kind of negative with more electrons, it's not a complete charge, but it's a partial charge. Those of you that have taken enough calculus to do partial derivatives know that we use the Greek letter delta for partial, and so fluorine has a partial negative charge, hydrogen has a partial positive charge. We indicate that with that delta minus and delta plus. Just as a recap, we've looked at this electronegativity before, but electronegativity up and to the right, fluorine, our most electronegative element, and generally speaking, the nonmetals are more electronegative than the metals. Fluorine paired with something like lithium is an ionic bond, but still all it is a difference in electronegativities. Fluorine is 4, lithium is 1, so that's a difference of 3. Hydrogen fluoride we just wrote as a polar covalent bond. That has an electronegativity difference of 2. What's the cutoff between something that's polar covalent versus something that's completely ionic? How do we know that that electron has been transferred just versus being shared unequally? Well, it's sort of an arbitrary cutoff, but if we look at the difference in electronegativity, so delta En, if that difference is less than 0.4, then we consider this to be nonpolar covalent. So an electronegativity difference of 0.4 or less is nonpolar covalent. If it's between 0.5 and 2, then we consider it polar covalent. So HF, the example I just gave, is just on the edge of being polar covalent. Anything greater than 2, we consider that to be an ionic bond. And so if we look here, here's our electronegativity difference of 2, right? Everything to the right of that is for sure ionic. Everything to the left of that has some polar covalent character and some ionic character. So lithium fluoride up here at 3, he's ionic for sure. But lithium bromide here, lithium chloride, lithium iodide, all of these are a little bit polar covalent, a little bit ionic. This is a continuum rather than discrete topics, right? And then all these guys down here, right? These are all polar covalent, or remember this here is our cutoff. And so these are what we consider nonpolar. Okay. All right. So do some good practice with those. Let me know if you have any questions, and we'll see. That's the intro to Chapter 9. Take care.